Okay, this is chapter 13, lesson 4. This is the last lesson in chapter 13. You should have seen an assignment post this morning that goes along with this lesson. So if you want to open up that assignment, you can kind of work through that as we're going through this together. You will need a calculator as you go through this. Hopefully what I'm doing here will give you a good idea of what we're looking at, but this is the last bit of information for chapter 13. So this is actually called colligative properties, which is a kind of a fun word to say there. And colligative properties are ones that are going to depend on the amount of solute that's in a solution. And so we're going to talk about mainly boiling point elevation and freezing point depression. It has to do with vapor pressure lowering. These two are kind of connected, and the vapor pressure lowering is not as big a deal as boiling point elevation and freezing point depression. Remember that an ion is an atom with an electrical charge, like sodium is an ion and chlorine is an ion, and together they make up a crystal lattice of oppositely charged ions like this. And so you have your big chlorines and your little sodiums. And so this crystal lattice together in a three-dimensional formation, repeating in every direction, we call that an ionic compound. All right, so just to give you a little bit of a refresher there. So solutes affect the physical properties of the solvent. So if you have water, we know the physical properties of water is that it freezes at 0 degrees Celsius and it boils at 100 degrees Celsius. If it's pure H2O, that means there's nothing in there but water. But when you start adding things in here, like little ions or little bits of particles, solutes, the physical properties of the water actually begin to change just a little bit. And so these changes, these physical property changes, are called colligative properties. Okay, they're called colligative properties, and the identity of the dissolved particle does not matter. And so it's kind of interesting how two different solutes can dissolve into water and have the same effect. So it's not really the identity, rather, but the number of particles. And obviously in chemistry, anytime we're talking about the number of particles, we're talking about the mole. Now there's two types of solutes that we need to be familiar with. We have solutes that are electrolyte solutes, and we also have non-electrolyte solutes. Electrolyte solute is something like sodium chloride. If I have a sample of sodium chloride and I were to place it into water, inside the water, if I zoomed in here, I would have sodium ions and chlorine ions floating around in there. Now what's important about this is one NaCl is actually two ions. We have one for the sodium and one for the chlorine. So together that makes two ions. Whereas over on this side we have a non-electrolyte solute like sugar. And so if I have a sample of sugar and I place it into water, and I were to zoom into it, they would just be sugar molecules. Sugar, sugar, sugar. And so for every 1 mole of a non-electrolyte, this equals 1 mole of particles in the water. Whereas an electrolyte, for 1 mole of an electrolyte, is going to equal a multiple number of ions, or multiple number of particles. So if I were to have something dissolve in water like Mg3N2 magnesium nitride, I would have to count this up. So there are 3 magnesiums and 2 nitrogens, which means there's 5 total ions. So for every 1 mole of Mg3N2, it equals 5 moles of ions. Okay, and so that's an important aspect here to remember, because when we're talking about colligative properties, it has to do with the number of particles, not with their identity. We don't care if it's an electrolyte or a non-electrolyte, we just want to know. So 1 mole of an electrolyte gives 1 mole, whereas a non-electrolyte is typically going to give more than 1 mole. Which means non-electrolytes are not as effective in colligative properties as electrolytes. And we'll see how that plays out later. Ionic compounds are further categorized by whether or not they are strong or weak electrolytes. Compounds that dissolve readily and produce many ions are called strong electrolytes. Compounds that produce just a few ions, or they're not very soluble, are called weak electrolytes. Typically, we would show you a strong versus weak electrolyte in the lab. If you guys remember, I had this little contraption that was a light bulb. Let's see if I can, this light bulb here, and it had these 2 little posts that came down, and so this, if we were in the lab, I would show you in a strong electrolyte like NaCl, the light bulb lights up really, really, really bright, and in a weak electrolyte like vinegar, it lights up just a little bit, and that's just because there's fewer ions in a weak electrolyte and many ions in a strong electrolyte. So if you have a whole bunch of ions, you have a lot of electricity being conducted, therefore a bright light. If you have few ions, you only have a little electricity being conducted, so a weak light, or just not very bright. All right, so let's look at colligative properties. The first colligative property that we'll look at that we're actually not going to do much with is vapor pressure lowering. Vapor pressure lowering is due to the number of solute particles in solution, and because it's due to the number of, we call it a colligative property. The presence of the molecules and ions in the solution are going to affect the amount of attraction between solvent molecules. So let's remember, if I have a sample of water and the water is going to become a vapor, in other words, it's going to get removed as a gas. So whenever you have a liquid, in this state it's liquid, up here still water, but it's a gas. In order for it to do that, this guy right here has to gain enough energy to overcome the force of attraction that it has with other water molecules. Remember those intermolecular forces. So we have this is a slightly positive, this is a slightly negative, and you have these intermolecular forces happening. And in order for this water molecule to become a gas, you have to have enough energy to break this bond right here. Well, when you have solutes in there, as we can see in this bottom here, if you have solutes in here, this solute starts to cause attraction to it, and so you have a change in the amount of attraction. So in a sample of water, each water molecule is only attracted to a couple water molecules around it, whereas this guy, this sugar molecule, is going to attract lots and lots and lots of waters, and then they are going to attract each other. And so because of this, this is going to change the amount of attraction. But it also changes how many water molecules can get to the surface. Because we're not boiling this, there's no fire underneath this thing, then in order for the water to become a gas, gases have to hit the top of it. That's evaporation. And so the little guys at the top will get so much energy that they'll shoot up into the air as a gas. Well, if you have sugar in here taking up some of this surface area, then you're not going to have as much of the water becoming a gas. And so we say that the vapor pressure is going to be lowered. In other words, it's not producing as much vapor. Well, if that's the case, if you have less vapor, you actually end up having a greater chance to, you're going to have a greater amount of energy needed to cause the water to become a gas when you heat it, because you have so much more attraction between the solute particles and the solvent. Consequently, it takes more energy to get the water to be a gas. So just in the exact same discussion, more energy for it to get to be a gas, that means that the boiling point, which we're going to say BP, the boiling point increases. So pure water boils at 100 degrees Celsius. And every pure substance has a defined boiling point. However, if you have a solute in the water will actually boil at a temperature higher than 100 degrees. If you put salt in water when you're cooking pasta or cooking some other dish, that actually causes the water to get higher than 100 degrees. And so therefore things will cook a little bit faster. Not a ton faster, but a little faster. And we call this colligative property boiling point elevation. Now remember, it has to do with the number of particles. Well, the number of particles is called the mole, right? Well, when we look at the number of moles, we can actually put this into an equation, and we can say that the change in temperature is going to be equal to a constant, we're going to call it the boiling point elevation constant, times the molality. Remember, molality is moles of solute over kilograms of solvent. All right, so moles of solute over kilograms of solvent. For non-electrolytes, the value of the, this should say boiling point, because that's what we're talking about here. The boiling point elevation is directly proportional to the solution's molality. For ionic compounds, the number of ions is more than that of its formula unit, and we've already talked about that. For example, 1 mole of sodium sulfate here is going to be 3 moles of ions, so we'd have to multiply by 3. So to do this, we take this little equation here, delta T equals K times molality. This table here is just common boiling point elevation constants. Or sorry, these are the constants, here you go, and these are the common boiling points. All right, so we'll use this information, so we're going to do one together, and then after we do one together, then you can do some on your own. So this says 75 grams of sugar is added to 100 grams of water. What is the new boiling point of the water? Well, remember, the delta T is equal to K sub B times molality. Well, if I have 75.0 grams of C12H22O11, I need to turn that into molality. Well, if I know the grams of C12H22O11, I can find that I have a certain number of moles of C12H22O11. Okay, so I'm just going to convert this guy into moles. So that's 342.34 grams. That gives me 0.2191 moles. Well, I need to know the molality, so 0.2191 moles of solute over 0.100 kilograms of water. I got that from this guy right here, 100 grams of water. So that means it's 2.19 molal solution. Well, if I just plug that into my equation, delta T equals K sub B times molality. So delta T is equal to the K sub B of water is 0.512 times 2.19 times, and I get delta T equals 1.12. All right, so that is delta T, but it's not the new boiling point. The new boiling point is the old boiling point plus how much it went up, which was 1.12. So the new boiling point here is 101.12 degrees Celsius, and that is my answer. So this guy goes here, and I add it to the original boiling point. So that's how you do boiling point elevation. So here's another one. We're gonna try another one here real quick. This one is 75 grams of salt in water. This one's going to be very similar to the first one, except it's salt. So we have to take into account the 2 moles of ions, 1 for sodium and 1 for chlorine. So it starts out exactly the same, 75.0 grams of NaCl. And for every 58.43 grams of NaCl is 1 mole of NaCl. Now here's where the electrolyte part comes in. For every 1 mole of NaCl, I have 2 moles of ions, 1 for the Na and 1 for the Cl. So I'm going to take 75 divided by the molar mass times 2. And so I get 2.57 moles divided by 0.100, and that gives me 25.7 molal. So now I'm going to say delta T is equal to 0.512 times 25.7, and I get that delta T is equal to 13.1. So 100 plus 13.1 gives me 113.1 degrees Celsius. All right, so that's the boiling point elevation with a electrolyte. This is the key step right here. So if you're following along on the worksheet, now you can do numbers 5 and 6 on the worksheet, which are practicing through boiling point elevation. So go ahead and pause the video and work on those two. All right, freezing point depression. This is our last colligative property. So in the same way that the ions or the solute particles in the water or in a solvent cause a change in the properties of that solvent, causing the boiling point to rise, it also has an effect on the freezing point. In order for something to freeze, the particles have to arrange themselves in a regular repeating pattern. Well, when you add a solute to something like water and it gets in between the water molecules have a hard time forming their regular repeating pattern, which means you have to cool them down colder than you usually do to get them to freeze. We can figure this out mathematically in the same way, that delta T is equal to a constant, and so it's going to be K sub F times the molality, because it's still the number of moles that's playing a role. So the molality is what we'll use to do that. Here's freezing points of some common substances, and here's their freezing point constants. Now you may have experienced this property, this freezing point depression, if you've ever made homemade ice cream. You put salt in ice cream and it causes not salt in ice cream, but you put salt in the ice around the ice cream in a homemade ice cream maker, and the ice around the ice cream maker gets below freezing. In fact, it gets about 12, 13 degrees below freezing. And by doing that, you can actually get the ice cream to set up a lot faster than trying to put it in a freezer. All right, so we're using the exact same problem, except now we want to figure out what is the new freezing point of water. So we're going to do the same thing, and we're just going to work it through again. So 500 grams of sugar. And we remember that it's 342.34 grams of sugar is 1 mole. And so we'll solve 75. And we get 0.2191 moles. We're going to divide it by 0.100 again, because it's the same amount of water, and I get 2.191 mole. So that's little m. All right. So I'm going to say that delta T is equal to K sub F times the molality. So delta T equals 1.86 times 2.191. And I get delta T is equal to 4.07. Now remember, this is freezing point depression. So I'm going to take 0 degrees Celsius and I'm going to subtract 4.07. So I get negative 4.07 degrees Celsius. So if you put sugar in water, it gets cold. So a soda will be colder than a glass of water with ice in it. And that's because the sugar in there dissolved into the water molecules actually, or dissolved into the water solution, actually makes the freezing point go down. And so when you put ice in it, it actually gets colder than 0 degrees. We can do the same thing. This time the salt is sodium sulfate. And so we're going to say 75 grams of sodium sulfate in Na2SO4. So 75 grams. All right, that's 142.03 grams is 1 mole. And for every 1 mole, I have 3 ions. And that's because there's 2 here, and the sulfate makes a third. So that's 3 total ions. So 75 divided by the molar mass times 3 tells me it's 1.58 moles divided by my 0.100 grams gives me 15.84 molal. And so we're going to do the same thing. 1.86 times 15.84, and I get 29.46, so we'll say 29.5. This is in water, so 0 degrees Celsius minus 29.5 is negative 29.5 degrees Celsius. So that's my answer for that guy. All right, so you've seen 2 of those. So now you can do numbers 7, 8, and 9 on the worksheet. So you guys can go do that guy. If you're having trouble with those, feel free to show up at office hours tomorrow. It'll be at 10 a.m. You can also email me and set up another time if you need to get together at another time to ask for questions. As far as the class goes, if you're keeping track of the class calendar, you'll see that on Thursday we're going to do a review worksheet. I'll hold office hours on Friday, and then you guys will have your Chapter 13 test next Monday, a week from today. So I hope everyone's doing well, everyone's staying healthy, and if you have any trouble, I'll see you tomorrow at office hours. If not, get this assignment done. It's due by midnight tomorrow night on Wednesday.